Good morning, students. Screen is visible, students. Screen is visible, please.
Yes, sir, visible.
We have solved up to problem number 6. Today we'll start with the problem number 7. Okay. So all of you please note down the problem number 7. All of you write problem number 7. Take 2 minutes time. Write the diagram as well. Over, students? Over? Written or still writing?
Writing, sir.
Okay. I think you all written. Shall we proceed?
Yes, sir.
Okay. So just go through the problem. A post-tension beam of rectangular section 200 mm wide and 400 mm deep is 10 meter long, carries an applied load of 8 kN per meter, uniformly distributed on the beam. It is a UDL. The effective pre-stressing force in the cable is 500 kN. Pre-stressing force is given. The cable is parabolic with zero eccentricity at the supports and maximum eccentricity of 140 mm at the center of the span. It is a parabolic cable with eccentricity at the middle span as 140 mm and at the support as 0. It is asked to find principal stresses at the supports, and there is one more question. What will be the magnitude of the principal stresses at the supports in the absence of pre-stress? If pre-stressing is not induced into the beam, then what will be the stresses? That is the question. Okay, we will solve one by one. First question. Before that, you write some given data. Other than geometric properties, what are the things given that you write? Pre-stressing force is given. Applied load, live load is given. Live load is equal to solution. Live load is given as 8 kilonewton per meter. Then effective pre-stressing force P is given as 500 kilonewton pre-stressing force. P is equal to 500 kilonewton, that is 500 Newton. Okay. Then what else is given? Eccentricity and all given, that is written in the figure only. Okay. Now we will go with the first question to calculate principal stresses at the supports. First one. Principal stresses at the support. Okay, we have the formula, right? We have the formula. That formula you write it, and whatever the required parameters to be determined, that you find and substitute, you will get the answer. Okay, so we know the formula for finding the principal stresses, that is sigma max or sigma minimum is equal to fx plus fy divided by 2 plus or minus half of root of fx minus fy whole square plus 4 tau v square. Okay, you find one by one. First you find fx horizontal pre-stress, fx horizontal pre-stress, horizontal pre-stress fx is equal to p by a. Area of cross section we can find it, a is equal to b into d. Width of the beam is 200 and depth of the beam is 400. 200 into 400, (80,000 mm square). Therefore, horizontal pre-stress Fx is equal to, the pre-stressing force is given as 500 kilonewton. 500 into 10 power 3 divided by cross-sectional area 80,000. Okay. What is horizontal pre-stress? Tell me.
6.25.
6.25. 6.25 Newton per mm square. Then what else is required? Fy is required, a vertical pre-stress, and there is no vertical tendons given in the beam. Therefore, Fy will be 0. Fy is equal to vertical stresses equal to 0. Then Fx is over, Fy is over. What else is required? We need a shear stress tau v, right? To find tau v, we have the formula. Tau v is equal to, what is the formula? Vu into Ay bar divided by I into B is the formula. Okay. Now we need shear force which is acting at the support. Okay, we need shear force which is acting at the support, and in the problem the live load is given. Self weight of the beam should also be considered, right? First you find the self weight or dead load of the beam. Live load is given. The dead load plus live load will give the total load. That using that total load we will find the shear force at the support. Okay. Therefore, the dead load of the beam is given by dead load of beam is equal to, the cross sectional area is 0.2 into 0.4, that is 200 mm by 400 mm. 0.2 into 0.4 into density 24. So what is the dead load?
1.92.
1.92 kilonewton per meter. Then live load on the beam is given. Live load on beam is equal to 8 kilonewton per meter. Therefore, the total load is equal to 1.92 plus 8, 9.92 kilonewton per meter. Okay. Now we came to know about what is the total load which is acting on the beam. Now we can find shear force, right? Shear force at the support. For that, you write a small diagram. The intensity of load is 9.92 92 kilonewton per meter. The span of the beam is, what is the span of the beam given? 10 meter. Span of the beam is given as 10 meter. Is the span. Now you can find reaction at the support, right? Therefore, the reaction at the support is given by WL by 2. Intensity of load is 9.92 into 10 divided by 2. What is the answer?
$49.6 kilonewton.
Yes, 49.6 kilonewton. Here we did not do the factorization of the load, right? Factor load we did not consider. Even if you consider, your answers will be considered, okay? Without considering, only if you are doing the solving the problem, both the cases will be considered, okay, while doing the evaluation. Okay, in some textbooks, factor load is considered, and considering the factor load only, the analysis of the beam is performed. In some other textbook, without doing the factorization, they have done the calculation. But in your examination, it is left to you. Okay, even you can take factor load, or as it is, whatever the direct load it is coming, by taking that load only, you can perform the analysis. And my suggestion is, if the problem is a analytical problem, if you are doing the analysis of the beam, better not to consider factor load. Okay, if you are doing design, then you can consider the factor load. This is my suggestion. Okay, in your examination, if he asked to perform the analysis, means if he asked to find the principal stresses like that, then what you do is, without multiplying 1.5, you do the calculation. Okay. In the next coming sessions, there are one more variety of problems, design for shear. Okay, they are design related problem. For design related problem, you consider the factor load and do the design. For analysis, better not to consider the factor load. Okay, whatever the total load, exact load that will come, no, that considering that load only you perform the analysis. Okay, is that clear, students? Because at the beginning, what I have done is, I think 2 to 3 problems I have considered the factor load. Okay, both answers will be considered, no problem. Okay, for both answers, the marks will be given, no issue. My suggestion is, for analysis problems, you don't consider factor load. For design problems, you consider the factor load. Okay. Now we got the reaction at supports, that is 49.6 kilonewton. VA is equal to 49.6 kilonewton. Now what else we have to find now? To find reaction at the support, we need to calculate the sum of the reaction at the support and the cable force, the force in the cable, that is vertical component of the cable. Okay, that you write now. Okay, it's a parabolic cable. So vertical component of the pre-stressing force is what? P sin theta, right? P sin theta. Therefore, total reaction at the support is VA plus VA minus P sin theta. Correct? Total reaction at the support is, or total shear force which is acting at the support is the sum of, okay, reaction at the support and the vertical component of the pre-stressing force. Okay. Therefore, it is VA minus P sin theta. Okay. So sin theta for parabolic cable, we know the formula for parabolic cable. For parabolic cable, the sin theta value is, what is the formula? 4E by L, correct? 4 into eccentricity at the midspan is 140 mm into 140 into 140 divided by 10 meters the span, 10,000. Okay. So by this you will get sin theta value
0.056.
is 0.056. Therefore, P sin theta value will be, or else directly calculate the net force. Therefore, net shear force VU at the support is equal to plus VA minus P sin theta. VA minus P sin theta. Therefore, VA is reaction 49.6 minus P is 500 kilonewton. 500 kilonewton into sin theta value is 0.056. 0.056. Therefore, what is the net shear force at the support?
$21.6.
Yes, 21.6 kilonewton. Okay, or 21.6 into 10 power 3 Newton. Okay, now you got VU, AY bar you need to calculate it. That is first moment of area or static moment of area. Write the cross section of the beam. Write the neutral axis. The width of the beam is 200 and depth is 400. 200 mm and depth is 400 mm. Then here it is 200. Now we calculate the first moment of this area. Okay. So if you find the centroid of this shaded area from the neutral axis, it will be at a distance of 100 mm, right? 200 divided by 2. Okay. Therefore, AY bar is equal to area of the shaded portion, that is 200 into 200 into centroidal distance Y bar, it is 100 mm. Tell me the answer. 2 into 2, 4. 6 zeros are there. Therefore, into 4, it will be equal to 4 into 10 power 6 mm cube. Am I right?
Yes, sir.
Then what else is required? We got VU, we got AY bar, moment of inertia we required. Find it. Moment of inertia. is equal to I is equal to BD cube divided by 12. 200 into 400 cube divided by 12. Tell me the answer.
1.066 into 10 power 9.
Yes, 1.066 into 10 power 9 mm4. Okay. Then width of the beam is now you can calculate shear stress, total shear stress. Therefore, tau V is equal to Vu into AY bar. Vu is 21.6 into 10 power 3 Newton. 21.6 into 10 power 3 Newton into AY bar value is 4 into 10 power 6. 4 into 10 power 6 divided by IB. I is 1.066 into 10 power 9 into width of the beam is 200. Therefore, the shear stress is equal to how much?
0.405.
0.405 Newton per mm square. Okay. Now you can find principal stresses, sigma max or sigma minimum. Every parameters are known. Now just substitute and get the answers. First you find sigma max. Sigma max is equal to fx plus fy divided by 2. Fx value is 6.25. Fy is 0. Therefore it is 6.25 plus 0 whole divided by 2 plus half of root fx minus fy 6.25 minus 0 whole square plus 4 tau v square into 0.405 whole square. How much?
$6.27.
Yes, 6.27, right?
Okay.
Newton per mm square. Okay, you are getting the positive answer, which is nothing but the compressive stresses. Compressive stress. Then find sigma minimum is equal to 6.25 plus 0 whole divided by 2 minus half of root 6.25 minus 0 whole square plus 4.405 whole square. Tell me the answer.
Minus 0.026.
Yes, minus 0.026 Newton per mm square, which is tension. Okay, to this, the first problem or the first question is over. Now we'll move on to the next question. Just look into the next question. What will be the magnitude of the principal stresses at the supports in the absence of pre-stress? Okay, here pre-stressing force P equal to 0 in second case. Okay, in second case pre-stressing force P equal to 0, right? Case B, principal stresses, problem number B, principal stresses in the absence of pre-stress. In the absence of pre-stress, that is P equal to 0. P equal to 0. Use the same formula. We know that sigma max or sigma minimum is equal to fx plus fy divided by 2 plus or minus half of root fx minus fy whole square plus 4 tau v square. Okay, fx is 6.25 Newton per mm square that we have earlier determined already. I'm sorry. Here precessing force P equal to 0, no? That is why it becomes 0. Fx equal to P by A. P by A. Here precessing force is equal to 0, therefore Fx becomes 0. Fy is, it is already 0. Fy is already 0. And tau v shear stress, again you write the formula and perform the calculation. And tau v shear stress is equal to Vu into Ay bar divided by Ib. Okay, we know the reaction at the support. Reaction at the support Va is equal to how much it was? Reaction at the support 49.6 kilonewton. Now let us write the diagram once again. 49.6 kilonewton. Okay. Then we need P sin theta value. P sin theta value will be equal to 0 because precessing force P equal to 0. Therefore, P sin theta equal to 0 and P sin theta is equal to 0. Therefore, what is the net shear force which acts at the support section? Therefore, the net shear force, therefore, the net shear force is equal to Vu is equal to Va minus P sin theta. Therefore, Vu is equal to Va is 49.6 minus 0 is equal to 49.6 kilonewton. Okay. So as there is no precessing force, whatever the reaction to the support is there, no, that is only the shear force which is acting at the support section, right? 49.6 kilonewton only. Now you find tau v. Tau v is equal to Vu is 49.6 into 10 power 3 Newton. You can write one more step here, 49.6 into 10 power 3 Newton. 49.6 into 10 power 3 into Ay bar. Earlier we have already calculated. It is how much? 4 into 10 power 6. 4 into 10 power 6 Vu into Ay bar divided by Ib. Moment of inertia, how much it was? Moment of inertia is 1.066 into 10 power 9. 1.066 into 10 power 9 into B 200. What is the shear stress? Tell me.
0.93.
Yes, 0.93. 0.93 Newton per mm square. Okay. Now you find sigma max and sigma minimum for the second case. Therefore, sigma max is equal to fx plus fy divided by 2. Both are 0. 0 plus 0 divided by 2 plus half of root, again 0 minus 0 whole square plus 4 tau v square. Tau v is 0.93 square. I think you'll get same value, whatever that OV value is there. Okay. You'll get the same value, right? Because root 4 value is 2. 2 by 2 becomes 0. Sorry, 2 by 2 becomes 1. And 0.93 whole square. Root of 0.93 whole square is 0.93. You'll get the same answer. Therefore, 0.93 Newton per mm square. And sigma minimum is equal to 0 plus 0 divided by 2 minus half of root 0 minus 0 whole square plus 4 0.3 square. You will get minus 0.93. Correct? Sigma minimum is equal to minus 0.93 Newton per mm square. This completes the problem. Understood, students?
Yes, sir.
Any doubts you can ask. Okay. Shall we move on to the next problem? Okay. We'll solve the next one. Write it. Write the next problem. It is a problem on I section. Write the next problem. It is quite different problem that we'll solve. Over, students.
Yes, sir.
Okay, all of you could just go through the problem. A pre-stressed I section has the following properties. Area, total area of the I section is given, cross-sectional area. Second moment of area is given. Then second moment of area is what? What is the meaning of second moment of area? It is nothing but moment of inertia. Okay, moment of inertia. Then static moment about the centroid is given. Static moment about the centroid means what? Static moment about the centroid. It is AY bar. Okay, static. You are taking moment of area about the centroid. Okay, that is why it is called a static moment about the centroid. Therefore, it is called. It is nothing but AY bar only. Okay, AY bar only. Don't get confused. AY bar is given. Thickness of web is given. And it is said that it is pre-stressed horizontally by 24 wires of 5 mm diameter and vertically by similar wires at 150 mm centers. Okay, here pre-stressing is given in both horizontal direction and vertical direction. Okay, in the horizontal direction there are 24 number of wires of 5 mm diameter. Okay, and in vertical direction the same diameter bars, that is 5 mm diameter bars, are spaced all along the length of the beam at 150 mm center to center. Okay, you go through the next step, next point. All the wires carry a tensile stress of 900 Newton per mm square. It may be a horizontal wire or vertical wire. All the wires are carrying a tensile stress of 900 Newton per mm square. That is pre-stress in the wires is given. Okay, pre-stress in the horizontal wires and vertical wires is given as 900 Newton per mm square. Okay, and it is asked to calculate the principal stresses at the centroid when the shearing force of 80 kilonewton acts on this section. Even the shear force also given. Okay, shear force is also given. So using all this data, we need to find the principal stresses. Okay, solution. First you write all the given data, whatever it is given in the problem. Area of cross section is given A. Area of cross section A equal to 55 into 10 power 3 mm square. Then second moment of area, which is nothing but AY bar. Okay, second moment of area AY bar is equal to 189 into 10 power 7. 189 into 10 power 7 mm. Sorry, second moment of area, moment of inertia, right? Moment of inertia. Better I'll write one more step here. second moment of area is equal to, it's nothing but moment of inertia. I equal to what is the value? 189 into 10 power 7. I equal to 189 into 10 power 7 mm4. Okay. Then static moment about centroid, which is nothing but AY bar static moment about centroid is equal to AY bar. It is given as 468 into 10 power 4. 468 into 10 power 4. It is mm cube. Change in the okay. It is given in terms of mm cube only. 468 into 10 power 4 mm cube. The thickness of web is given. Thickness of web BW is given as how much it is? 50 mm. 50 mm is the thickness of web. Then what else is given? It is pre-stressed horizontally by 24 wires of 5 mm diameter. Calculate the total area of pre-stressing steel. There are 24 number of wires having 5 mm diameter. What is the total area of cable? Area of cables is equal to area of one bar is pi d square by 4 into 5 square by 4 into 24 numbers. What is the answer? Tell me.
471.
Yes, 471.23 mm square. The stress in the cable is given. Tensile stress. It is 900 Newton per mm square. Stress in the cables is equal to 900 Newton per mm square. You know area of cables, you know stress in the cable, you can find pre-stressing force. Am I right? Therefore, pre-stressing force P is equal to stress into area. Stress is 900 into area of cable 471.23. Tell me the answer.
424.107 kilonewton.
Yes, 424.10 into 10 power 3 Newton, or 424.1 kilonewton. Then what else is given? Shear force is given. Shear force Vu is equal to Vu is equal to 80 kilonewton. Okay, this is all given data. Okay, now question is to find principal stresses. Am I right? Calculate the principal stresses at the centroid when a shearing force of 80 kN acts on the section. We need to find principal stresses. We know the formula to find the principal stresses. Write it first. Sigma max or sigma minimum is equal to fx plus fy whole divided by 2 plus or minus half of root fx minus fy whole square plus 4 tau v square. Okay. Now you find one by one. First fx horizontal pressures. Horizontal pressures fx is equal to, what is the formula? P by A. P by A. Here A is area of I section, area of cross section, not area of the cables. Okay. So to find pre-stressing force, we have utilized area of cables. Here to find horizontal pressures, we need to use area of the section. Pre-stressing force we have already calculated, 424.1 into 10 power 3. 424.1 into 10 power 3 divided by area. It is given. It is given. Area of cross section, how much it is given? 55 into 10 power 3. Correct? 55 into 10 power 3. Tell me the answer.
7.71.
7.71, sir.
Yes, 7.71 Newton per mm square. Okay. Now, in the problem, you can see it is pre-stressed horizontally by 24 wires of 5 mm diameter and vertically by similar wires at 150 mm center to center. Okay. So there is vertical tendons also given. For that, we need to find Fy. Okay. Let us see how to find that Fy. Okay. It is clearly mentioned in the problem. Okay. The beam is pre-stressed both horizontally and vertically. Okay. Horizontally, you are all familiar with finding the fx. Okay, for horizontal cables. For vertical cables, let us see how to find the Fy, vertical pre-stress. Okay, let us see how to find vertical pre-stress. Okay. You just go through the problem. It is said that the vertical, what is the vertical reinforcement or vertical tendons given? They are having 5 mm diameter placed at 150 mm center to center. Okay. For that, I'll write the diagram now. Okay. If you write the diagram, then it will be easy to do the calculation. I'll write a small diagram. Okay. Here I have written web of the beam, just web of the beam. Okay. Flanges are not written. Whatever the diagram I have written, it is web of the beam. Okay. So in the problem, what he said that there is 5 mm diameter bars placed at 150 mm center to center all along the length of the beam. Like this. Okay. So this spacing is 150 mm. Okay. The spacing is 150 mm. Okay, 150 mm spacing and diameter of the bar is 5 mm. So we need Fy. Okay, I'll write the plan of the diagram, same diagram now. I'm writing the plan. It is 150 mm center to center. Okay. Now we need to find Fy, vertical pre-stress. Vertical pre-stress is equal to Fy is equal to, okay, again it is, again stress will be force by area P by A. Okay, now to calculate this vertical pre-stress, okay, what we will do is we will consider one particular bar. Okay, one particular bar. For one particular bar we will calculate the vertical pre-stress. So for one bar, the stress which is acting on the bar is given. What is the stress acting on the bar? It is tensile stress 900 Newton per mm square. Okay, so force pre-stressing force for one bar is equal to stress into area. Stress in bar is given as 900 Newton per mm square. 900 into area of one bar is 5 into 5 square divided by 4. Tell me the answer.
$17,671.45.
17,671.45 Newton. Okay. Now we have calculated pre-stressing force P for one bar. Now we will calculate area of cross section under one bar. Area of cross section under one bar. A equal to, see, this is the plan which I written. The area of cross section, the effective area of cross section for one particular bar will be here. The spacing of the bar is 150 mm center to center. If you are measuring stress for one bar by considering only one bar, area the force in that one bar is we have already determined, and area under that one bar will be half of the length on either side. Okay, half of the spacing on either side. So total the spacing of the bars is 150. Effective area. Okay, so half of spacing on either side becomes 75 and 75. So total length will be how much? 150 only. Total length will be 150 only, and thickness of web is given in the problem. BW. How much it is given? BW 50 mm. Here we mention it. Thickness of the web is 50 mm. 50 mm. Okay. Therefore, area under 1 bar is how much? Tell me. Area under 1 bar is how much now? Tell me, students.
7,500 mm square, sir.
Yes, it is 150 into 50 is area under 1 bar. Okay, 150 into 50. So 7,500 mm square. Understood, students? Any doubts here? Understood? Understood?
Yes, sir.
Okay, this is very simple thing. What I have done is to calculate the vertical pre-stress. I considered only 1 bar. Okay, area of 1 bar I considered. For pre-stressing force in 1 bar I have calculated, and area under 1 bar we have calculated, and pre-stressing force for 1 bar divided by area of cross section under 1 bar will give stress. Okay, so while calculating Fx we have calculated all the bars, pre-stressing force in all the bars divided by area of all the bars. Okay, sorry, here pre-stressing force, total pre-stressing force, full area of cross section. Okay, full area of cross section. Okay, because this pre-stressing force is calculated based on the total area of bars. Okay, but that is the difference. Okay, here what we do is pre-stressing force is calculated by considering all the bars all over the cross section. Okay, all over the cross section. Therefore, it is pre-stressing force divided by total cross sectional area. Okay, here as you are considering only 1 bar. Okay, you need to consider area under 1 bar only. Okay, I hope you all understood this. If you have any doubts, you can ask. Okay, now you can find Fi. This is only the important step here. Fi equal to, therefore Fi is equal to P by A 17,671.45 divided by 7,500.
$2.35.
2.35. Okay. So while measuring Fx, we have considered all the bars and full cross sectional area. While measuring Fi, we have considered only 1 bar and area under only 1 bar we have considered. That is the difference. Okay. So if you are known with what is the total number of bars along the length of the beam, you can calculate as like Fx. Here total number of bars it is not given in the problem. He has just given what is the spacing. He has just mentioned spacing of the bar and diameter of the bar. So if only spacing and diameter is mentioned, this is how we calculate the vertical pre-stress. Okay. If total number of bars is given, total number of bars multiplied by stress will give total force, and total force divided by total area of web in the plan will give Fi. Okay. So as only spacing is given, we need to follow this method. Only by considering 1 bar, we need to find the stress. Okay. Now Fx is known, Fi is known. Next tau v we have to calculate it. Shear stress. Tau v is equal to Vu into Ay bar divided by Ib. Vu into Ay bar divided by Ib, where V is the shear force. Shear force is directly given in the problem itself, 80 kilonewton. V is equal to shear force. V is equal to 80 kilonewton, which is nothing but 80 into 10 power 3 Newton. Even Ay bar is also given, right? No need to calculate it. Ay bar, how much it is? Ay bar 468 into 10 power 4. Ay bar is equal to 468 into 10 power 4 mm cube. Then moment of inertia is also given. That is second moment of area. How much it is? 189 into 10 power 7. 189 into 10 power 7 mm4. Then what else? B. What is B? B means how much here? Tell me. How much we have to take? Width of web. Okay, BW. How much it is? 50 mm. Okay. Nothing but BW only. Okay. See, because the pre-stressing steel is given in the web portion only. Okay. Pre-stressing steel is given in the web portion only. Even in the horizontal pre-stressing steel will be given in the web portion only. That is why we need to consider width of web, not the width of flange. Okay. Yeah, here width of flange is not given only. Even if it is given, don't get confused. You take width of web only. Okay. Now you can substitute to get the shear stress. Therefore, tau V is equal to Vu is 80 into 10 power 3. Ay bar is 468 into 10 power 4 divided by I is 189 into 10 power 7 into 50. Tell me the answer, friends.
$3.96.
Yes, 3.96 Newton per mm square. I think now you can calculate sigma max and sigma minimum. Fx is known, Fi is known, tau V is calculated, just calculate it. Therefore, sigma max is equal to Fx plus Fi whole divided by 2. Fx is 7.71, Fi is 2.35. 7.71 plus 2.35 divided by 2 plus half of root Fx minus Fi whole square. 7.71 minus 2.35 whole square plus 4 tau V square. 3.96 square.
$9.81.
How much? 9.81.
9.8.
Yes. Plus sign, which is nothing but compression. And sigma minimum is equal to 7.71 minus 2.35 whole divided, sorry, plus 2.35 whole divided by 2 minus half of root 7.71 minus 2.35 whole square plus 4 into 3.96 square. Tell me the answer. How much?
0.6.
Yes, 0.25 Newton per mm square. So this is also getting plus sign, therefore compression. Nature of stress is compression. Okay, this completes the problem. If you have got any doubts, you can ask. Shall we move on to the next one?
Yes, sir.
Okay. Problem number 9. Write it first. Take 2 minutes time. Write both the figures. I will explain later. Write as it is. Write the neat figure. Okay. Finished? Finished or still writing?
Finish, sir.
Okay, we'll solve. So it is also a quite different problem. You just go through it. This figure is not given. I have written as per the parameters given. Okay. A cantilever portion of a pre-stressed concrete bridge. Okay. It is a cantilever beam. In all previous problems, it was a simply supported beam, but in this problem, it is a cantilever beam. Okay. A cantilever portion of a pre-stressed concrete bridge with a rectangular cross section 600 mm wide and 1650 mm deep, 1650, 600 mm wide and 1650 mm deep, is 8 meter long. Length of the beam is, length of the cantilever is 8 meter and carries a reaction of 350 kilonewton from the suspended span of the free end. Okay, there is a force of 350 kilonewton at the free end. Okay, that force I have written together with a uniformly distributed load of 60 kilonewton per meter inclusive of its own weight. Okay, there is a UDL and there is a point load at the end of the beam. Okay, whatever the UDL given, it is inclusive of self load only. No need to calculate the dead load. It is inclusive of dead load only. 60 kilonewton per meter. The beam is pre-stressed by 7 cables, each carrying a force of 1000 kilonewton. Okay, there are 7 number of cables provided in the beam, and each cable are carrying a force of 1000 kilonewton. Each cable, of which 3 are located at 150 mm, 3 at 400 mm, and 1 at 750 mm from the top edge. Okay, the same thing I have written here. 3 bars located at 150 mm, 3 bars located at 400 mm, and 1 bar located at 750 mm from the top edge, not the bottom edge. Okay. Why from the top edge? Why from the top edge? What may be the reason? Here bars are provided from the top edge instead of providing from the bottom edge. What is the reason? Cantilever beam it is. Have you designed the cantilever beam? For cantilever beam, the tensile stresses are developed at the top fiber and the compressive stresses are developed at the bottom fiber. That is why for cantilever beams we will provide the bars at the top only. Okay. Let us see the question. Calculate the magnitude of the principal stresses at a point 550 mm. Okay, at a point 550 mm from the top of cantilever at the support section. That is the question. Okay. Now here, if you look into the previous problems, there were some parallel bars which were having some eccentricity at the center of the span and zero eccentricity at the support. Okay, their eccentricity was directly known. Okay, but here there are 7 number of bars, okay, placed at different spacing from the top fiber, means 3 bars are spaced at 150 mm from the top fiber and 3 bars are provided at 400 mm from the top and 1 bar is provided at 750 mm from the top. Okay, so for this condition we need to find the eccentricity. Okay, we need to find the eccentricity. What is eccentricity? Eccentricity is the distance between centroid of the precessing cables to that of centroid of the whole section. Okay, for that we need to first locate what is the centroid of precessing force. Okay, if there is a single set of cables provided at a single row, okay, provided in a single row, it was directly distance from center of this one row of cables to that of centroidal axis eccentricity. But here the bars are provided at different locations. First we need to locate centroid of the precessing force. After that you can find the eccentricity. Okay, to find the centroid of precessing force we have the formula. Okay, write it. Centroid of precessing force from top edge yt is equal to a1 y1 plus, there are 3 number of bars, 3 sets of bars or 3 rows of bars provided, 1 row, second row and third row. Okay, so we will find a1 means area of 3 bars and respective y1 distance centered of bars from the top fiber, and a2 y2 and a3 y3 we will find. First you write this formula. Centered of precessing force from top edge yt is equal to okay, I hope you all written the formula. Now first find a1. A1 is equal to area of first row of bars. Okay, diameter of each bar is how much given? Diameter it is not given, right? Diameter is not given. Okay, diameter is not given, just number of bars are given. Diameter is not given, but still we can find the location of the centroid, no problem, we will find it. What we'll do is we'll assume let area of 1 bar be A. Okay, we'll assume area of 1 bar as A. Okay, so there are 3 number of bars in first row, therefore A1 becomes 3A. Am I right? All the bars are having same diameter. If you assume area of 1 bar as A, area of first row of bars is 3A. And what about Y1? See, we are finding centroid of precessing force from top edge. So here Y1 is distance of centroid of first row of cables from the top fiber. How much it is? It is directly known, 150 mm. Y1 is equal to 150 mm. Are you understanding, students? Are you understanding? Please reply.
Sir, repeat, sir.
Okay, I'll repeat it, no problem. See, students, here in the previous problem we used to give directly the cable profile. Okay, cable profile eccentricity used to give directly. What is the eccentricity at the support? What is the eccentricity at the midspan? Used to directly give, but here in this problem it is not given. Okay, is not given. We have to find it. Okay, How to find it? Here the bars are located at different positions. Okay. First, what we have to do is we have to find centroid of the pre-stressing force. What is eccentricity actually? If we have if there is a bar pre-stressing bar, if this is the centroidal axis or the neutral axis of the section, the distance between centroid of pre-stressing force and neutral axis is nothing but eccentricity. Okay, distance between centroid of pre-stressing force and the neutral axis or the centroidal axis of the whole section is nothing but the eccentricity. Okay, here the bar, it is not positioned at a single location. Okay, it is not positioned at the single location. Here 3 bars are located at 150 mm, 3 bars are located at 400 mm, and 1 bar is located at 750 mm. Okay, for that purpose what we have to do is first we have to identify what is the centroid of all these bars. Okay, what is the centroid of all these bars? After knowing centroid of all these bars, distance between that centroid to centroid of the whole section will give eccentricity. Okay, in this way we have to find the eccentricity here. You got idea? You understood?
Yes, sir.
Now to find what is the centroid of all the bars, we have the formula. Yt is equal to, with respect to top fiber, we will find it A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3. There are three rows. The bars are provided in 3 rows. For each row, I have considered the area 1, area 2, and area 3. Okay. And one more important thing is here he has not given the diameter of the bar. Diameter of the bar is not given. That is why we will assume let diameter be A. Okay. If you assume diameter as A, then A1 becomes, there are 3 number of bars in a first row, 3A. Y1 becomes 150 mm from the top fiber. And A2 equal to how much? Now, area of second row of bar. A2 is equal to 3A. A2 equal to 3A. Y2 how much, tell me? Y2? Y2 how much?
400.
400. Correct. 400 mm. And A3 is equal to, there is only one bar in third row. Only A it is. A3 is equal to A. And Y3 is equal to how much? Distance of third row of bar from the top fiber. It is 750. Yes.
750 mm.
Yes. 750 mm. Therefore, Yt is equal to. Therefore, Yt is equal to means Yt represents distance of centroid of the bars from top fiber. A1 Y1, that is 3A into 150 plus A2 Y2, 3A into 400 plus A3 Y3, A into 750 divided by A1 plus A2 plus A3, that is 3A plus 3A plus A. Okay, you take A common in both the numerator and the denominator. Yt is equal to A into 3 into 150 plus 3 into 400 plus 1 into 750. All divided by A into 3 plus 1. A gets cancelled. You will get distance of centroid of the cables now.
$342.8.
342.8. You run it out to 343 mm. 343 mm. Okay. Now you got distance of centroid of cables from the top fiber. That is at a distance of 343 mm from the top fiber. That you mentioned it in the diagram. I hope you already mentioned. Okay. Now you can find the eccentricity, right? You can easily find eccentricity now. Eccentricity is nothing but distance between centroid of the cable to that of centroid of the whole section. This distance. Okay. So centroid of the whole section is total depth divided by 2. Total depth is 1650 divided by 2. If you do around 825, you will get minus 343. If you do, you will get this eccentricity. Here I have done that calculation. Okay. 160 whole divided by 2 minus 343. If you do, you will get the required eccentricity. Therefore, eccentricity is equal to E is equal to half of this depth. Okay, from here to here it is 1650 divided by 2. 1650 divided by 2 minus 343. If you do, you will get the required eccentricity. Minus 343. How much you will get?
482 mm.
Is 482 mm. Is there any doubts, students, in this step? Finding the eccentricity?
No, sir.
Okay. Now, it is said that 7 cables, each carrying a force of 1000 kilonewton. Each cable is carrying 1000 kilonewton, and there are 7 number of cables. Okay. Therefore, the total pre-stressing force is equal to, total pre-stressing force is equal to, there are 7 cables, each carrying 1000 kilonewton force. Number of cables. Okay. So what is the total force you will get?
7,000.
7,000 kilonewton or 7,000 into 10 power 3 Newton. Okay, that is P value. Okay, now we got the eccentricity, we got the pre-stressing force. Okay, the rest of the calculation we'll do it in the next class. Okay. Take the other ends.